There is a question I've been sitting with for a long time. Not a complicated question, not a scientific one, exactly. Just a quiet, strange little question that showed up one evening when I was watching the sun go down over the horizon. The sky was turning gold and then pink, and then a deep, soft blue. And I was watching the sun disappear, the way you do when you're tired and you've stopped thinking about anything in particular. And I thought, what's up there? Not above the clouds, not above the atmosphere, but above the sun itself, above the star, in the direction the sun's north pole is pointing right now as you listen to this. Not to the left or right, not in the direction we orbit, but directly above, directly below. What is actually there? I realized I had no idea. And when I started looking into it, I found something I didn't expect. Not emptiness, not a simple answer, but a story. One of the most beautiful, strange, and quietly astonishing stories in all of science. A story that changes how you see the sky, changes how you feel about your own existence on this little blue world. Welcome to Sleepy Science Stories. I'm so glad you're here tonight. If you're new here, this is what we do. We take the universe's biggest questions and we slow them down. We let them breathe. Because the most extraordinary discoveries don't need to be loud or rushed or overwhelming. The ones that stay with you, the ones that settle into something real, those are best absorbed gently in the dark, right here on the edge of sleep. Tonight we have 2 hours together. No hurry, nowhere to be. Just you and the universe and a question that most people never think to ask. Get comfortable. Let your body settle. Let your shoulders drop. Take one slow breath in and let it go completely. Oh, we're leaving now. Quietly. And before we go anywhere, I need to tell you something that stopped me cold the first time I heard it. You have never, not once in your entire life, left the sun. The sun is larger than you think. Much larger. When most of us picture the sun, we picture a disk. A bright, golden circle hanging in the sky. Something you can cover with your thumb if you hold it up at arm's length. Something that rises in the east and sets in the west and warms your skin on summer afternoons. But the sun does not end where its light becomes visible. Not even close. The sun has an outer atmosphere. A region of charged particles and magnetic fields that extends outward in all directions, far beyond the visible disk. Far beyond Mercury and Venus, past Earth and Mars and Jupiter, past Saturn and Uranus and Neptune, past Pluto, past the distant frozen objects of the outer solar system, and out into the space between stars. This region is called the heliosphere, and it is the true body of the sun. Think of it this way. You can see someone's hand, but their body doesn't end at the surface of their skin. There's warmth radiating from them. There's a field of influence around them. The heliosphere is the sun's field of influence, its extended body, and we live inside it. Every planet you've ever learned about lives inside the sun's heliosphere. Every spacecraft ever launched. Every comet that has ever burned across our night sky. The Apollo astronauts who walked on the moon, the rovers on Mars, the Hubble Space Telescope floating in Earth orbit. All of it, every single human creation that has ever left this planet, has done so while remaining inside the outer body of our sun. I find this quietly breathtaking. We talk about exploring space as though we're leaving home. But in the most literal physical sense, we haven't left yet. Not really. We're still inside the sun. And tonight, we're going to find the edge of it. And then we're going to go beyond. But first, we need to answer a simpler question. Does space have an up and a down? Stand outside on a clear night. Look up. Up is obvious. It's where the stars are. It's where the moon hangs, where planes disappear, where the darkness deepens into something vast and still. Down is the ground. Solid, certain, real. But here's the thing. The moment you leave Earth, up and down stop meaning anything at all. In space, there is no floor. There is no ceiling. There's no gravity pulling you toward a single center unless you're near something massive like a planet or a star. Astronauts on the International Space Station eat upside down. They sleep on the ceiling. They drift sideways through corridors. None of it feels wrong because none of it is wrong. In space, every direction is equal. So when we ask what sits above the sun, we're actually asking a human question, not a cosmic one. We're choosing a direction and giving it a name. And I think that's worth sitting with for a moment, because it says something interesting about us. We are creatures who need orientation. We need an up and a down. We need a map. Even when the territory has no such thing, we invent one, because without it, the vastness becomes too much to hold. Scientists agreed long ago to use a shared reference point. They chose the plane of Earth's orbit around the sun, the flat invisible disk that Earth traces as it circles the sun each year. This is called the ecliptic plane. And by convention, north is the direction above this plane, toward the constellation Draco. South is below it, toward the constellation Dorado. It's not a cosmic truth. It's a human decision, a beautiful, practical fiction that gives us a map to navigate something our minds weren't evolved to comprehend. And tonight, we'll use that map to drift upward and downward from the sun, out through the layers of our solar system, and into the deep, quiet, dark beyond. Before we go anywhere, let's take one slow look at the sun itself. From a safe distance, floating in space with no atmosphere between you and the light, the sun is not what you expect. It isn't the flat golden disk of a summer afternoon. It is a sphere, a vast, churning, living sphere of plasma, 1.4 million kilometers across. So large that you could fit more than 1 million Earths inside it with room to spare. It is roughly 4.6 billion years old. It formed from a collapsing cloud of gas and dust in a quiet region of the Milky Way galaxy. Gravity pulled the cloud inward over millions of years. Pressure built, temperature rose, and deep in the core, hydrogen atoms began fusing into helium, releasing energy. The sun ignited. It has been burning ever since. Every single second, the sun converts around 600 million tons of hydrogen into helium through this process of nuclear fusion. In doing so, it loses a tiny fraction of its mass as pure energy. That energy begins a remarkable journey. Deep in the core, where temperatures reach 15 million degrees Celsius, a photon of light is born. But it doesn't simply fly outward into space. The core is so dense, so packed with particles, that the photon immediately collides with something, gets absorbed, re-emitted in a random direction, absorbed again. It wanders, it drifts, slowly, over what scientists estimate to be somewhere between 10,000 and 170,000 years. That single photon makes its way from the core to the surface, 100,000 years, give or take, to cross a single star. And then, once it breaks free of the surface, it travels at the speed of light across 150 million kilometers of empty space and arrives at your window in 8 minutes. That warmth on your face this afternoon? It began its journey before modern humans walked the earth. before the last ice age, before our ancestors painted on cave walls. The light that touches you today is genuinely ancient. The sun has layers, and the further out you go, the stranger it becomes. The part of the sun we can see, the bright disk in the sky, is called the photosphere. It isn't a solid surface. The sun has no solid anywhere. The photosphere is more like the visible top of a very deep, very turbulent ocean of plasma, a layer about 500 kilometers thick where light finally escapes into space. When scientists observe it closely through specially filtered instruments, the photosphere is alive with motion. Dark regions called sunspots drift slowly across its face, areas where intense magnetic fields suppress the flow of energy, making them slightly cooler and therefore darker than the surrounding surface. Around them, the surface bubbles with structures called granules, rising columns of hot plasma that cool at the edges and sink back down, each one roughly the size of a small country. Right now, in mid-2026, the sun is in an unusually active state. Solar cycle 25, which peaked in October 2024, turned out to be nearly twice as powerful as scientists predicted. Sunspot numbers exceeded 200, far above the forecast of around 115. We are now in the declining phase of that cycle, but the sun remains restless, active and bright and expressive in ways we didn't fully anticipate. Above the photosphere floats a thin, luminous layer called the chromosphere. It is only visible to the naked eye during a total solar eclipse, when the moon covers the bright disk and reveals a delicate ring of pinkish light. The word chromosphere means color sphere, named for that rosy glow. But above the chromosphere, something deeply puzzling begins. The corona is one of the most beautiful mysteries in all of science. Beyond the chromosphere, the sun's atmosphere stretches outward into space in a ghostly crown of plasma called the corona. Best seen during a solar eclipse, it appears as pale, luminous streamers reaching outward from the hidden disk like the petals of an enormous cosmic flower. The corona is impossibly hot. The sun's visible surface sits at around 5,500 degrees Celsius. You would expect the temperature to fall as you move away from that surface, the way a campfire gets cooler as you step back from it. But the corona doesn't do that. Instead, the temperature rises, dramatically, shockingly. The corona reaches temperatures of 1 to 3 million degrees. Some active regions exceed 10 million. The further you get from the sun's surface, the hotter the atmosphere becomes. Scientists call this the coronal heating problem. It is one of the oldest unsolved questions in astrophysics. There are theories: magnetic waves carrying energy outward from the surface, tiny explosions called nanoflares releasing bursts of heat. But no single answer has fully explained it. The corona holds its secret warmly, glowing at a temperature we can measure, but not quite explain. This is one of the things I love most about science. The sun is the closest star to Earth. We have been studying it for centuries, and it still surprises us, still holds questions we can't answer. There's something comforting about that, I think. The universe is not a solved puzzle. It is an ongoing conversation, and we have recently sent someone to listen more closely. The Parker Solar Probe, launched by NASA in 2018, is the closest any human-made object has ever come to a star. It has flown through the sun's outer corona, not near it, through it, sampling the plasma directly, feeling the heat. In March 2026, it completed its 27th close approach to the sun, skimming to within 6.2 million kilometers of the solar surface while traveling at approximately 430,000 kilometers per hour. That is fast enough to travel from New York to London in under 30 seconds. At that speed, At that distance, the Parker Solar Probe is touching the sun. What it has found there is reshaping our understanding of the corona, of the solar wind, and of how stars work. It has detected structures in the corona called switchbacks, sudden reversals in the magnetic field that release bursts of energy. It has helped scientists observe magnetic reconnection events, moments where opposing field lines snap and merge, releasing enormous amounts of stored energy into the surrounding plasma. Each close approach, the probe survives. Each time, it brings back something new. A small heat-shielded messenger carrying our questions into the fire, and from that fire, something pours outward in all directions. The corona does not end cleanly. It thins and fades and eventually becomes something else entirely, something called the solar wind. A constant stream of charged particles, mostly electrons and protons, flowing outward from the sun in every direction at speeds ranging from 400 to 800 kilometers per second. Imagine that. Not a breeze, not a gust. A river of particles, invisible and unceasing, pouring outward from the sun at hundreds of kilometers every second, every minute, every hour of every day. It has been flowing since the sun was born. It will flow until the sun dies. The solar wind streams past Mercury and Venus. It flows past Earth and Mars. It rushes past the giant planets, past Jupiter and Saturn and their moons. It races outward past Uranus and Neptune, past Pluto and the other distant frozen worlds, past everything we have ever named and visited. And it carries with it the sun's magnetic field, stretched and pulled outward into an enormous invisible shape surrounding our entire solar system. This shape is the heliosphere. And here is where I want to share something that surprised me, something the science textbooks of a decade ago got wrong. For a long time, scientists believed the heliosphere was shaped like a comet, a round front end facing the direction of our solar system's travel through the galaxy, and a long trailing tail stretching behind us, dramatic, elegant, and as it turns out, probably not quite right. In recent years, data from NASA's IBEX spacecraft, the Interstellar Boundary Explorer, has revealed something stranger and more interesting. The heliosphere appears to be shaped more like a deflated croissant. Two lobes, one above the ecliptic plane and one below, with no long trailing tail at all. A bubble that is squashed and asymmetric, shaped by the pressure of interstellar space pushing back against the solar wind. A deflated croissant, surrounding our entire solar system, containing every world we have ever known. I find this particular detail wonderfully humbling. We live inside a croissant-shaped bubble of sunlight, drifting through interstellar space. And we only figured out its true shape within the past few years. The universe keeps revising itself. Now, let us begin to rise above the ecliptic plane, above the flat disk where the planets orbit, upward slowly in the direction scientists call north, toward the northern ecliptic pole. As you rise, the solar system begins to reveal its shape. From above, it looks like a disk. The planets orbit the sun in roughly the same flat plane, tracing ellipses that together form a wide, thin structure. Earth, Mars, Jupiter, Saturn, all of them circling in this shared plane, patient and steady, drawn by the sun's gravity into their long curved paths. From above, you can watch them all at once. Neptune, taking 165 years to complete one slow orbit. Mercury, swift and close, completing its year in just 88 days. Between them, the others, each in their own rhythm, their own quiet dance around the central fire. Beyond Neptune, the disk continues but grows sparse. Out here lies the Kuiper Belt, a wide region of frozen objects and dwarf planets, including Pluto. It extends from about 30 to 50 times the Earth-Sun distance and contains thousands of icy bodies, remnants of the early solar system that never gathered into a full planet. Pluto is here. Cold and small and surprisingly complex, with mountains of water ice and plains of frozen nitrogen. It was discovered in 1930, reclassified as a dwarf planet in 2006, and photographed up close for the first time in 2015 by the New Horizons spacecraft. In those images, Pluto appeared not as a featureless dot, but as a world, with geology, with atmosphere, with a heart-shaped plain of nitrogen ice that captured something in all of us. From above this plain, the sun at the center looks small, steady, like a bright lamp left on in an empty house at the end of a very long road. And then, something happened in June of 2025 that changed everything about this view. For as long as we have studied the sun, we have studied it from the side. From Earth's vantage point, which orbits in the ecliptic plane, we have always seen the sun's equator face on. Its north pole and south pole have remained hidden from us, tilted away, impossible to observe directly. No spacecraft in history had ever looked down at the sun's poles with proper imaging instruments. The Ulysses mission flew over the poles between 1990 and 2009, but it carried no cameras. It could measure the solar wind, sense the magnetic field, but it could not see. And then Solar Orbiter changed that. The European Space Agency's Solar Orbiter has been slowly tilting its orbit, year by year, climbing higher above the ecliptic plane. In March 2025, it reached an orbital inclination that allowed it to observe the sun's south pole from above for the first time. The images were released to the public in June 2025. The first photographs ever taken of the sun's south pole from directly above. I remember reading about this and having to set down what I was doing and just sit quietly for a moment, because this was not a small thing. Humans have been watching the sun for our entire existence. Cave paintings, ancient observatories, centuries of telescopes. And for all of that time, we had never seen the top and bottom of our own star. And when we finally did, what we found was unexpected. The south pole of the sun was a mess. At solar minimum, the poles of the sun are typically organized. They carry a single, dominant magnetic polarity, either all north or all south, like the simple poles of a bar magnet. But the images from Solar Orbiter showed something different, both positive and negative magnetic polarities swirling together at the south pole in a complex, chaotic tangle. Scientists believe this is related to where we are in the solar cycle. During solar maximum, the sun's global magnetic field breaks down and reorganizes. The poles lose their simple structure. The magnetic field becomes complicated, turbulent, and beautifully disordered. We caught the South Pole in the middle of a transformation, a moment of cosmic uncertainty, the sun rearranging itself. By December 2026, Solar Orbiter will increase its inclination further to 24 degrees above the ecliptic, giving us an even clearer view of the poles than we have ever had. We are only just beginning to see the top and bottom of our own star. After all this time, let's rest here for a moment. You have come a long way tonight. The heliosphere surrounds you, that warm, deflated croissant of solar wind and magnetic fields. Below you, the disk of planets traces its patient circles. Ahead, in the direction we are calling north, space opens outward into something vast and still. Your breath is slower now, I think. The sounds around you have softened. You're floating above the solar system, above the sun's south pole that no human eye had seen until just 1 year ago, in a darkness that is not frightening, just wide. The sun behind you is still bright enough to be the brightest light in the sky, but it is already smaller than it looks from Earth. From here, you could cover it with your thumb. Let that land for a moment. The thing that fills our sky, that sets the time of day, that determines seasons, that allows every living thing on Earth to exist, the sun itself, can be covered by your thumb from a short distance in space. That's not a reason to feel small. That's a reason to feel something else entirely, something that doesn't quite have a name. A kind of quiet awe, mixed with gratitude, mixed with wonder. The recognition that you are part of something immeasurably large and that you get to exist inside it. Your eyes can close if they want to. You don't need to go anywhere. You are already there, drifting in the quiet above the sun, in a silence that hums with invisible fields and ancient light. In part 2, we will drift further, past the heliosphere's edge, into interstellar space. We'll follow the travelers from between the stars who have passed through our solar system unannounced. We'll reach the Oort Cloud, that enormous distant shell of sleeping comets that wraps our solar system in all directions. And we'll talk about what it means to live not just inside the sun, but inside the galaxy itself. But for now, simply be here. The universe is very large and very old, and tonight it is very quiet. And you are exactly where you are supposed to be. We are still rising, above the ecliptic plane, above the flat disk where the planets trace their long, patient circles, past the first layers of the heliosphere, past the region where the solar wind still blows warm and steady. The sun is below us now, not gone, never quite gone, but smaller, already smaller than it looks from Earth. A brilliant point of light among the dark. Take a slow breath. Let your body settle a little more. There is no hurry here. The universe has been doing this for 13.8 billion years, and it is perfectly content to continue at its own pace while you rest. We are going to the edge of home tonight, and then beyond it. Every journey has a boundary. Ours is called the heliopause. There is no wall, no gate, no sign marking the boundary. The edge of the sun's influence is not a line you cross so much as a place where two vast forces meet and press against each other in a long, slow standoff. On one side, the solar wind, that constant outward breath from the sun, streams of charged particles flowing at hundreds of kilometers per second in every direction. On the other side, the interstellar medium, the material that fills the space between stars, pressing inward from every direction with its own quiet pressure. Where these two forces meet and compress, scientists call it the heliosheath, a turbulent, churning zone of slowing particles and tangled magnetic fields. And beyond the heliosheath, where the solar wind finally stops entirely, overwhelmed, absorbed, dissolved into something older and larger than itself, that is the heliopause. The true edge of the sun's reach, the true boundary of home. We know this boundary exists not just in theory, but because we have sent something across it. Something small and extraordinary. Something built by human hands nearly half a century ago. On September 5th, 1977, a spacecraft launched from Cape Canaveral. It was called Voyager 1, and it has been traveling ever since. As of mid-2026, Voyager 1 has been moving through space for nearly 49 years. It crossed the heliopause in August 2012 and became the first human-made object to reach interstellar space. It is currently more than 25 billion kilometers from Earth. A signal traveling at the speed of light, the fastest anything can travel, now takes over 23 hours to bridge the distance between us and it. Almost a full day. Just for a message to arrive. Just for a whisper to cross the gap. And yet, we are still in contact. As of 2026, Voyager 1 is still sending data home, still functioning after nearly 5 decades in space. Its power, generated by the slow decay of radioactive plutonium, is fading. But NASA engineers expect it to continue communicating into the early 2030s with careful management. But I want to tell you something about Voyager 1 that moved me when I first read it. In November 2023, something went wrong. Voyager 1 began sending back garbled data, unintelligible signals, corrupted transmissions that made no sense to the engineers monitoring it from Earth. For months, the team struggled to understand what had happened to a spacecraft 24 billion kilometers away, knowing that any message they sent would take 22 hours to arrive and another 22 hours for the response to return. Nearly 2 days for a single exchange. Eventually, in early 2024, they pinpointed the problem. A tiny portion of memory in the spacecraft's flight data computer had been corrupted, possibly by a cosmic ray, possibly by simple age. About 3% of the onboard memory had gone bad, and it was scrambling everything the spacecraft tried to transmit. The fix required something that had never been done before. Engineers, including some who had come out of retirement to help, rewrote the spacecraft's software and uploaded the new code across billions of kilometers of space. They deleted obsolete data from a Jupiter flyby in 1979, code that had been sitting unused for 45 years, to make room. They waited 2 days for each exchange. They tested, they adjusted, they waited again. And in May 2024, Voyager 1 came back. All 4 remaining science instruments resumed transmitting clear, clean, coherent data from the edge of the solar system, flowing across 24 billion kilometers as if nothing had happened. I think about the people who did that. The engineers who spent months solving a problem on a machine they could not touch, could not see, could not reach, communicating through messages that took 2 days to send and receive. Doing something that had no precedent, something that had never been done, and that most people on Earth will never hear about. Quietly extraordinary. The kind of thing humans do when they care deeply about something, even something as small and far away as one aging spacecraft drifting through interstellar space, alone. Voyager 2 went the other way. While Voyager 1 traveled northward above the ecliptic plane, heading toward the galactic north, its twin left Earth on August 20th, 1977, 2 weeks earlier, and took a different path. Voyager 2 used the gravity of 4 planets, Jupiter, Saturn, Uranus, and Neptune, to swing through the outer solar system on a grand tour that has never been repeated and may never be repeated, because the planetary alignment that made it possible occurs only once every 176 years. On November 5th, 2018, Voyager 2 crossed the heliopause from the south, entering interstellar space below the ecliptic plane. 6 years after its twin, 2 probes, moving in opposite directions, one above the sun, one below, both carrying the same cargo, a golden record. Each Voyager carries a 12-inch gold-plated copper disc, chosen and assembled by a team led by the astronomer Carl Sagan. On it, music, Johann Sebastian Bach, Beethoven, Chuck Berry's Johnny B. Good, a Navajo night chant, a pygmy girl's initiation song, the sounds of rain and surf and wind and crickets, greetings spoken in 55 human languages, including one from a child, and the sound of a mother speaking to her newborn. These records are drifting through interstellar space right now, above the sun and below it, moving in opposite directions into the galaxy, carried by two small machines that will outlast everything we have ever built. If no one finds them for 1 billion years, the records will still be there. If no intelligence in the universe ever finds them, they will drift on in silence, forever. And I think that matters anyway. I think the act of sending them matters, regardless of outcome. We chose, as a species, to introduce ourselves to the universe with music and rain and a mother's voice, not with weapons, not with warnings, not with claims of territory or power, with laughter, with Bach. There is something in that choice that I find quietly beautiful, and on nights like this, I hold on to it. On August 25th, 1990, Voyager 1 turned around. It was already 6 billion kilometers from Earth, heading outward. Its mission to the planets was complete. There was no scientific reason to look back. In fact, the engineers worried that pointing the camera toward the sun might damage it. But Carl Sagan had been asking for it since 1981. Asking, requesting, arguing that we should take one photograph of Earth from that distance before the cameras were turned off forever. It took him 9 years to get permission. And on February 14th, 1990, Valentine's Day, Voyager 1 turned its camera back toward home and took 60 photographs that were assembled into a mosaic of the solar system. In one of those photographs, Earth appeared as a single pixel, a pale blue dot, barely distinguishable from the scattered bands of sunlight the lens was catching. A mote of dust suspended in a sunbeam, as Sagan would later describe it. That photograph is called the pale blue dot, and Carl Sagan, looking at it, wrote something that has stayed with me since I first encountered it. He wrote, "Look again at that dot. That's here. That's home. That's us." From 6 billion kilometers, which is not far at all in cosmic terms, the Earth is invisible to the naked eye. Everything that has ever happened in human history, every great empire, every war, every moment of joy or suffering or love or cruelty, every person who has ever lived, all of it occurred on a surface so small that a camera barely registered it. That image does not make me feel insignificant. It makes me feel something else entirely. Something like relief. Something like the recognition that the things which divide us are genuinely, measurably, astronomically small. That from any perspective beyond our own, we are one thing, one pale blue dot, together. And now we are going further from that dot than any camera has ever looked back from. We are heading out toward the edge of the solar system's outermost shell, toward the Oort Cloud. But first, we are passing through something remarkable. Our solar system does not sit in average interstellar space. If you could zoom out and look at the region around our sun, you would find that we live inside a cavity, a vast, roughly spherical region where the normal density of interstellar gas has been cleared away, leaving a bubble of hot, thin, nearly empty space. Scientists call it the local bubble, and it is approximately 1,000 light-years across. Here is how it formed. Roughly 14 million years ago, this region of the galaxy was home to a cluster of massive stars. Massive stars live fast and die violently. They burn through their hydrogen in millions of years rather than billions, and when they die, they explode as supernovae. Over millions of years, around 15 of these stars in our neighborhood exploded, one after another. Each explosion sent a shock wave outward at thousands of kilometers per second, sweeping gas and dust ahead of it, compressing the interstellar medium into a shell around the blast zone. 15 supernovae, each one clearing space, the shock waves overlapping and reinforcing each other until the region had been largely evacuated. What remained was the local bubble, a cavity blasted into the galaxy by stellar death. Hot inside because supernovae pour energy into the gas, thin because the matter had been swept outward, clear because the dust that normally dims our view of distant stars had been pushed to the edges, and we live inside it. Our solar system sits near the center of the local bubble. Not because we were there when the explosions happened. Our sun is 4.6 billion years old, and the local bubble only formed 14 million years ago. But because the sun has been drifting through the galaxy on its own slow orbit and happened to drift into this cleared region, we are, in a sense, camping in a crater made by ancient stellar explosions. And at the edges of the local bubble, compressed by those ancient shockwaves, dense clouds of gas and dust have accumulated. And inside those clouds, new stars are being born right now. The explosions that cleared our neighborhood also created the nurseries where new suns are igniting, destruction creating the conditions for birth, the universe doing what it has always done. The space directly above and below the sun, for hundreds of light years in each direction, is this bubble, cleared, open, a window out to the rest of the galaxy. Because of ancient catastrophe, we can see further. And through that window, 3 strangers have passed in the space above and below the sun, in the interstellar medium beyond our heliosphere. Objects drift between star systems. Most of them drift forever, unobserved. But occasionally, one falls toward our sun at just the right angle to pass through our solar system, close enough to observe. We have now seen 3 of them. The first arrived in October 2017. Astronomers at a telescope in Hawaii noticed an object moving through the solar system on a trajectory that made no sense for something born here. It was moving too fast, at the wrong angle. Its path, when calculated backward, led to interstellar space. They named it Oumuamua, a Hawaiian word meaning messenger from afar arriving first. And the more scientists studied it, the stranger it became. It had no tail, no visible outgassing, no cloud of material around it, despite being close enough to the sun that any ordinary comet would have been visibly active. It appeared reddish and possibly elongated, shaped like a cigar or a flat disk. And as it departed our solar system, it accelerated. Slightly, but measurably. Faster than the sun's gravity alone could explain. For years, the acceleration was unexplained. Some scientists proposed hydrogen gas being released invisibly. Others suggested it was a thin sheet of material pushed by sunlight. One paper, more poetically, raised the possibility of an artificial origin, though most scientists considered this the least likely explanation. By 2024, a leading hypothesis had emerged. New research suggested Oumuamua was experiencing nozzle-like venting of volatile gases from beneath its surface, releasing material as it warmed near the sun. This could explain the acceleration without requiring anything exotic. The gases may have been too sparse and too diffuse to form a visible tail, which would explain why we saw none. Oumuamua, the best current science suggests, was likely a comet. But unlike any comet we had ever seen from our own solar system, a visitor with its own chemistry, its own history, its own story that we could only partially read. It passed through and left. We never got close enough to know it fully. The second visitor arrived in August 2019. Gennady Borisov, an amateur astronomer in Crimea, noticed it first. This one was clearer. It had a tail. It had outgassing. It was unmistakably a comet. But its orbit, calculated backwards, led to interstellar space. It was named Borisov in his honor. Borisov was in many ways more reassuring than Oumuamua. Its chemistry, analyzed by telescopes from Earth, was surprisingly similar to comets from our own solar system. The building blocks of planetary systems, it seemed, were not unique to us. Comets form around other stars the way they form around ours. The raw materials of worlds are common. The universe is generous with its ingredients. And then, on July 1st, 2025, a third visitor was detected. 3I/Atlas, named for the survey telescope that spotted it. This one came from a direction suggesting a long journey through the galaxy. Researchers tracing its origin using galactic orbit models determined that it likely came from a stellar system between 7 and 12 billion years old, far older than our own sun. Some observations from the James Webb Space Telescope suggested it might be nearly as old as the universe itself. Think about what that means. An object that formed in a stellar system born when the universe was young, perhaps only 1 or 2 billion years into its existence, has been drifting through interstellar space for billions of years. It predates our solar system by billions of years. When Earth was forming, 3I/Atlas was already ancient. When the dinosaurs appeared, it was ancient. When humans first looked up at the night sky, it was ancient. And in July 2025, it passed through our neighborhood. Briefly, without stopping. What has it seen? We cannot know. It carries no record. It cannot speak. But it has drifted through more of the universe's history than almost anything we have ever encountered. All 3 of these visitors came from the space above and below our sun, from interstellar directions. They fell inward from beyond the heliosphere, crossed through our solar system on paths shaped by billions of years of galactic travel, and continued outward on the other side. They did not stop, but their passing changed something for us. They reminded us that the space above and below the sun is not static. Things move through it. Objects travel between stellar systems across unimaginable distances and unimaginable time. The space between stars is a thoroughfare. We just never noticed until recently. And surrounding all of this, like the most patient thing in existence, is the Oort Cloud. We have been drifting outward for a long time now. Past the heliopause, through the local bubble, into the interstellar space where our 3 visitors traveled before us. But we have not yet reached the furthest boundary of the solar system. That boundary is the Oort Cloud. It is not a disk, the way the Kuiper Belt is. It is a sphere, a vast, hollow sphere of icy objects surrounding the sun in every direction, above, below, and all around. It begins somewhere between 2,000 and 5,000 times the Earth-Sun distance, and extends outward to perhaps 100,000 to 200,000 times that distance. The outermost reaches of the Oort Cloud may stretch nearly halfway to the nearest star. No spacecraft has ever reached it. No telescope has directly imaged an object within it. We know it exists because of what it sends us. Comets. When something disturbs the outer Oort Cloud, a passing star, a gravitational nudge, an encounter with another drifting object, some of those distant icy bodies begin to fall inward. Slowly at first, then faster. Drawn by the sun's gravity over thousands of years, they spiral inward through the dark, crossing the outer solar system, warming as they approach the inner planets. Ice sublimates. Gas and dust stream outward. A tail forms, always pointing away from the sun, swept back by the solar wind. A comet. The great comets of history came from here. The ones that blazed across ancient skies and were recorded by civilizations with no understanding of what they were seeing. They came from directly above and below the solar system, from that vast distant sphere, falling inward after billions of years of stillness, burning briefly in the inner solar system before swinging back out into the dark. Halley's Comet returns every 75 to 76 years. The last time it was visible from Earth was 1986. The next time will be 2061, and astronomers note that the 2061 return will be better positioned than 1986 was, more visible, better placed in the sky, a longer and cleaner view for those who will be there to see it. Some people alive today will watch Halley's Comet in 2061. Children who are young right now, drifting off to sleep on quiet nights just like this one, Voyager 1, which has been traveling for nearly 49 years and is the most distant human-made object ever launched, will not reach the inner edge of the Oort Cloud for approximately another 300 years. It will not fully exit the Oort Cloud for perhaps 30,000 years. Let that land softly. 30,000 years. Moving continuously, and still inside our solar system's outermost shell. The solar system is so much larger than we imagine. The Oort Cloud is the roof and the floor of home. Trillions of objects, not thousands, not millions. Trillions of icy bodies drifting in long, slow orbits at the very edge of the sun's gravitational reach. Patient, still, in a silence so complete that the sun, from out there, is nothing more than a bright star, the brightest star in the sky, but a star. Most of these objects will never move. They will orbit in that silence for billions of years, for the remaining lifetime of the sun, for the end of the solar system itself. But occasionally one falls, and for a brief time something ancient and cold becomes briefly, brilliantly alive in the inner solar system. A reminder that the stillness is not emptiness, that the dark shell above and below the sun is full, waiting, patient beyond anything we can truly imagine. I think of the Oort Cloud the way I think of very old forests, where every tree is centuries old and the whole place has a kind of presence that you feel but can't quite explain, where silence is not absence but accumulation, where time has been doing its work so long that the landscape itself seems to breathe. The Oort Cloud is time made solid. 4.5 billion years of solar system history, preserved in ice, floating at the edges of home. And it wraps us in every direction, above, below, all around, without preference, without boundary, the same sphere of ancient ice and rock above the sun's north pole as below its south. Floating here, at the outer edge of home, everything looks different. The sun is far below now, a bright point of light, still the brightest thing in the sky from here, but a star among stars nonetheless. In the right conditions, from the right angle, you could cover it with your thumb. The planets are invisible, too small, too dim, too distant to see without instruments. Earth, the place where everything you love exists, is somewhere in the direction of that bright point. So small it cannot be seen. A pale blue dot, as Carl Sagan described it, though from out here even that dot has vanished. And yet everything is there. Everyone you have ever known. Every piece of music you have ever loved, every conversation that has mattered, every ordinary morning, every meal shared, every night spent exactly like this one, breathing slowly in the dark with your thoughts going quiet. All of it in that invisible direction, on that invisible world. From out here, whatever separates people on Earth, whatever divisions feel large and real and important down there. From this distance, those divisions are smaller than a single pixel. Everything human is happening on a surface too small to see from the edge of our own solar system. I don't say that to make it feel meaningless. I say it because I think it makes it feel precious, specific, held, the opposite of meaningless. Everything is happening in such a small place, with such brief lifetimes, and with such astonishing richness. The universe is vast, life is small, and somehow, improbably, there is music. There is rain. There is a mother speaking to her child. Let yourself hold that for a moment. You are floating at the edge of home. The sun is a star below you. The galaxy stretches in every direction. The Oort Cloud surrounds you, its ancient icy silence pressing gently from all sides. Your breath is slow. Your body is heavy and warm. The thoughts that were busy when you began have grown quieter now, more like shapes in fog than anything sharp. This is where we rest tonight, not in the darkness of nothing, but in the fullness of everything. At the edge of our solar system, in the outermost shell of home. Far away on that invisible pale blue dot, someone is making tea. Someone is watching stars appear through a window. Someone is drifting off to sleep, just as you are now. Everything is very small. Everything is very far away. And right now, you don't need to think about any of it. Just rest. Just drift. The Oort Cloud has been here for 4.5 billion years. It will be here while you sleep. Something is about to change. We have been drifting outward for a long time now. Past the solar wind, past the heliopause, past the ancient icy silence of the Oort Cloud. We have floated in the interstellar medium where our sun is just a star and watched objects older than our planet pass through our solar neighborhood without stopping. And somewhere along the way, without quite noticing when, the scale shifted. The solar system is no longer the frame. The frame is now the galaxy. Take a slow breath. Let your eyes stay closed. What I am about to show you is best seen from the inside of your own mind, because no telescope has ever captured it whole. No human being has ever seen it from the outside. We are going to look at our home the way no one ever has, from far enough away that the sun itself becomes invisible, and from close enough that every star we pass has a name. If your body is already heavy and your thoughts already quiet, let them stay that way. You don't need to follow every detail. You can let the words drift through you like light through water, present but not pressing. The journey continues whether you are fully awake or already half in a dream. We are rising now, past the boundary of the solar system, past the last traceable influence of our sun, into something larger than anything we have named so far tonight. There is a secret at the center of our galaxy, and we finally saw it in 2022. For decades, astronomers suspected something enormous sat at the heart of the Milky Way. Not a star, not a nebula, something that consumed everything near it and emitted nothing. They suspected it because of the stars closest to the galactic center, stars that move in ways nothing ordinary could explain. Stars wheeling around something invisible at extraordinary speeds, completing their orbits in decades instead of millions of years. The object was called Sagittarius A star, written with a symbol, said as a word, named for the constellation that marks the direction of the galactic center from Earth. A supermassive black hole. Mass, approximately 4 million times that of our sun. Not spread across space, but compressed into a region smaller than our entire solar system. A density so extreme that the laws of physics, as we normally understand them, begin to break down at its edge. a point where space and time themselves bend in ways that no human intuition was built to imagine. For most of our history, we knew it was there, but could not see it. Black holes emit no light. They consume it. And the center of the Milky Way is hidden behind the densest concentration of gas and dust in the galaxy, opaque to visible light, observable only in other wavelengths. Then came the Event Horizon Telescope. Not a single instrument, but a collaboration. 8 radio telescope facilities positioned across 5 continents, including observatories in Hawaii, Chile, Spain, and Antarctica. By synchronizing their observations precisely and combining their data, they effectively created a telescope the size of Earth itself. The larger a telescope's aperture, the finer its resolution. An Earth-sized aperture means extraordinary resolution. The team had first succeeded in 2019 with a different black hole, the supermassive one at the center of the galaxy Messier 87, 55 million light-years away. That image, a glowing orange ring around a central darkness, became one of the most widely shared scientific images in history. But in May 2022, they released something even more significant for us. The first photograph of the black hole at the center of our own galaxy, Sagittarius A star. Our black hole, the one our sun has been orbiting for 4.6 billion years. It looked exactly as the physics predicted, a ring of glowing, superheated gas swirling around a dark center, orange and warm and alive with motion, surrounding an absence so complete it seemed almost deliberate. I remember seeing that image for the first time and just sitting with it for a while, because there is something particular about photographing the thing at the center of your own home, not a distant galaxy, not a theoretical construct, the black hole that your sun has been orbiting since the day the sun was born, photographed for the first time with instruments built by human beings in the few thousand years since we began writing things down, 26,000 light-years away. Patient and immense and ancient in a way that makes billions of years feel ordinary. And we finally looked it in the eye. Our solar system is not still. We tend to think of the sun as fixed, the anchor, the center around which everything else moves. And within our solar system, that is true. But the sun itself is in constant motion, has always been in motion, and will be in motion until the day it dies. The Milky Way is a vast, slowly rotating structure, a barred spiral galaxy with a long central bar of densely packed stars connecting 2 major spiral arms that sweep outward in great curves. It stretches roughly 100,000 to 120,000 light-years from edge to edge. It contains somewhere between 200 and 400 billion stars, each one following its own orbital path around the galactic center. Our sun orbits that center at approximately 220 kilometers per second. To put that in terms, the body can almost feel. That is 800,000 kilometers every hour. The Earth orbits the sun at about 30 kilometers per second. The sun moves through the galaxy more than 7 times faster than that. And one complete circuit, one full orbit of the galactic center, takes our sun roughly 225 million years. Astronomers call this a cosmic year, a galactic year. One unit of time so large that 20 of them span the entire age of the solar system. The last time our solar system was in the same position in the galaxy that it occupies tonight, the Triassic period had not yet begun. The Permian extinction, the worst mass extinction in Earth's history, had ended only a few million years before. The continents were still assembled into Pangaea, that single supercontinent, and the oceans were unrecognizable. No flowering plant had ever existed. No bird had ever flown, and the sun was already 4.3 billion years old, already halfway through its life, already shining with almost exactly the same light it shines tonight. We have been traveling the entire time, every second of every day of every year of human history, every conversation ever had, every book ever written, every night ever spent under the stars wondering about the stars. All of it occurred while the solar system swept through the galaxy at 220 kilometers per second, silently, continuously, without pause. You have never been still, not once in your life, not for a single moment. I find this one of the most quietly disorienting and quietly liberating facts in all of science. And as we orbit, we bob. This is something I come back to often, something most people never hear about, tucked inside the larger story of galactic motion. And I think it deserves a moment. Our solar system does not orbit the galaxy in a perfectly flat circle. As we move around the galactic center, we also drift upward above the dense central plane of the galaxy's disk, and then back down through it, and below it, and then upward again, like a horse on a carousel, rising and falling in a long, slow rhythm, while also moving in a great circle. The period of this oscillation is genuinely uncertain. Different models, using different measurements of the galactic disk's density and mass, give different answers. Current estimates range from roughly 30 to 70 million years for one complete up and down cycle. The amplitude, the maximum distance above or below the galactic midplane that we reach, is approximately 160 to 300 light years. Right now, our solar system is estimated to be somewhere between 50 and 90 light years north of the galactic midplane, drifting slowly upward, moving away from the densest part of the disk toward the thinner, quieter regions above it. Over the solar system's 4.6 billion year lifetime, we have crossed the galactic midplane many hundreds of times. Each crossing takes us through the denser regions of the disk. Denser regions mean more nearby stars. More nearby stars mean slightly different gravitational conditions reaching the Oort Cloud. And disturbances to the Oort Cloud mean more comets falling inward toward the inner solar system. Some researchers have proposed that this rhythmic crossing is connected to patterns in Earth's biological history, that the timing of mass extinctions over the past 500 million years shows a periodicity that might be explained by these galactic crossings. More comets inward means more impacts. More impacts mean more extinction events. The hypothesis is controversial. The statistical evidence is suggestive but not yet conclusive. Other researchers argue the periodicity is not real, or that the timing does not match as cleanly as the hypothesis requires, but the image it creates will not leave me. The idea that somewhere in the record of life and death on Earth, in the timing of the great extinctions that punctuate our fossil record, there may be an echo of the galaxy's rhythm, that the rise and fall of species on this small blue planet may carry, very faintly, the fingerprint of a bobbing motion measured in tens of millions of years. The galaxy has been rocking us, slowly, continuously, for billions of years, and we are only beginning to wonder if we can feel it. We have only recently learned to see our own home. For most of human history, mapping the Milky Way was impossible. We were inside it, looking outward in every direction without any high ground, any aerial view, any point of reference outside the structure we were trying to map. It was like trying to draw a detailed chart of a forest while standing inside it, surrounded by trees in every direction, with no ability to climb above the canopy. That changed with Gaia. The European Space Agency's Gaia satellite launched in December 2013 and has spent over a decade doing something previously unimaginable. It has measured the precise positions, distances and motions of nearly 1.8 billion individual stars in the Milky Way. Not estimated, not approximated, measured. Each star located in three-dimensional space with a precision that, for nearer stars, corresponds to measuring the thickness of a human hair from several hundred kilometers away. What Gaia has revealed is a galaxy more complex, more dynamic, and more historically rich than our earlier models suggested. The disk of the Milky Way is not flat. It is warped at the edges, bent upward on one side and downward on the other. And this warp is precessing, slowly rotating around the galaxy's center at a detectable rate. The outer disk twists and curves in ways no simple model predicted, and the stars of the Milky Way are not arranged uniformly. Gaia found stellar streams, long rivers of stars moving together through the galaxy, the gravitational remnants of smaller galaxies that the Milky Way absorbed billions of years ago. It found stars born in other galaxies, now permanently incorporated into our own. It found ancient stars in the halo that carry the chemical signatures of their birth in systems long since dissolved. But perhaps the most striking discovery is this. The Milky Way has scars. Billions of years ago, a smaller galaxy called the Sagittarius Dwarf Galaxy passed through the Milky Way's disk, not once, but multiple times. Each passage sent shock waves through the distribution of stars, creating waves and corrugations in the disk that propagate outward like ripples in a pond. Those ripples have not settled. They are still moving. Gaia has detected them, measured them, tracked them. The Milky Way disk is still vibrating from an ancient impact, still ringing from a collision that occurred before the dinosaurs walked the Earth. We are living inside a galaxy that has not fully recovered from its past. The stars above and below the galactic plane, the very region we are drifting through tonight, carry the imprint of that ancient collision, patterned and corrugated by forces that were set in motion billions of years ago. Above the galactic plane, the universe opens. Rising above the Milky Way's disk, above the dense, star-rich region where our sun resides, the air clears. The metaphor fails a little, because there is no air in space. But the view clears. Gas and dust thin dramatically. The great obscuring curtain of interstellar material that blocks our view through the galactic plane falls away. And in every direction above it, galaxies appear. Andromeda first, also known as Messier 31, our nearest large galactic neighbor. A barred spiral galaxy roughly similar in size to our own Milky Way, containing several hundred billion stars, located approximately 2.5 million light-years away. The light arriving from Andromeda at this moment left that galaxy 2.5 million years ago. When it began its journey, our ancestors were carrying stone tools across African grasslands. The word astronomy had not yet been invented. Agriculture was still 2.4 million years in the future. And that light has been traveling ever since, crossing the void between galaxies, until tonight it falls on a dark sky above a quiet planet. Andromeda is moving toward us, pulled by gravity. In approximately 4.5 billion years, the two galaxies will begin to merge in a process spanning hundreds of millions of years. Astronomers have modeled this merger in detail. In their simulations, when Andromeda arrives, the night sky of whatever world exists in our solar system will be transformed. The combined galaxy will stretch across the sky as a brilliant band of light. New stars will form from compressed gas clouds. Old ones will be redistributed into new orbits. The Milky Way and Andromeda will become one thing, one merged elliptical galaxy that astronomers have already named Milky Way. But long before that merger happens, there is a larger structure to understand. A structure so large that when scientists first described it in 2014, many people found the scale simply impossible to hold. We live inside Laniakea. Using velocity data gathered from thousands of galaxies, a team of astronomers in 2014 mapped the flow of matter in our region of the universe. Not just the positions of galaxies, but their movements, where they were heading, what they were being drawn toward. What they found was that our local group of galaxies, the cluster that includes the Milky Way, Andromeda, and dozens of smaller companions, was not drifting randomly through the cosmos. It was flowing, moving steadily toward a common center, along with tens of thousands of other galaxies, all of them drawn together by the gravity of something immense. The researchers traced those flows to their convergence point and mapped the full extent of the structure. What they found was a supercluster 520 million light-years across, containing approximately 100,000 galaxies and a mass equivalent to 100 million billion suns. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. The Milky Way sits near Laniakea's outer edge, in a quiet corner of this enormous structure. The great attractor, which astronomers had been puzzling over for decades, is now understood to be Laniakea's center of mass, the place all the flows converge, the gravitational heart of our cosmic home, and our local group is drifting toward it at roughly 630 kilometers per second. Not because we are falling exactly, but because gravity, applied across hundreds of millions of light years, over billions of years, adds up. Laniakea surrounds us in every direction, above the sun and below it, extending outward for 520 million light years. This structure flows and moves and gradually changes shape over cosmic time. We are not just inhabitants of the Milky Way, or even of the local group. We are, in the largest sense, inhabitants of Laniakea, residents of an immeasurable heaven we only discovered 11 years ago. I think about what it means to suddenly learn the address you have always lived at. Not just the street, not just the city, not just the country, but the continent. Laniakea is our continent, and we only found out it existed in 2014. Below the galactic plane, other worlds wait. Below the Milky Way's disk, visible from Earth's southern hemisphere as two soft clouds of light drifting away from the galactic band. The Magellanic Clouds orbit our galaxy at distances of roughly 160,000 and 200,000 light-years. The Large Magellanic Cloud is our nearest galactic neighbor. It contains hundreds of millions of stars and one of the most intensely star-forming regions known to science, the Tarantula Nebula. If the Tarantula Nebula were as close to Earth as our own Orion Nebula, 1,300 light-years away, it would dominate our night sky entirely. It would be bright enough to cast shadows, bright enough to be visible in daylight. As it is part of a faint smudge of light, visible only from the southern hemisphere on a clear, dark night. Beautiful and quiet, a reminder that distances in the universe are not just spatial, but experiential. The most spectacular thing in our cosmic neighborhood is hidden from most people on Earth simply by the accident of which hemisphere they were born in. Below the galactic plane also means looking back in time, because in space, distance and time are the same thing. Light travels at a fixed speed. Further away means older light, and the clearest views from above and below the galactic disk extend further, in time as well as space, than any direction through the disk itself. This is where the James Webb Space Telescope has done its most extraordinary work. James Webb looked into the deep past and found something unexpected. the James Webb Space Telescope launched on Christmas Day, 2021. After 6 months of traveling to its observing position and another 6 months of cooling, unfolding, and precise calibration, it released its first science images on July 12, 2022. The world paused for a moment. In one of those images, a patch of sky no larger than a grain of sand held at arm's length contained thousands of galaxies, each containing hundreds of billions of stars, each between 4.6 billion and 13.4 billion light-years away. The most distant objects in that image were showing us the universe as it existed just a few 100 million years after the Big Bang. In the years since, JWST has made discoveries that have genuinely surprised the scientific community, not just refined our models, but challenged them. In 2024, it detected what researchers called the cosmic vine, a massive filament of 20 galaxies stretching 13 million light-years from end to end, seen as it existed 12 billion years ago, when the universe was less than 2 billion years old. A structure of that scale and maturity should not have had time to form so early. And yet there it was, patient and enormous in the ancient universe, defying our expectations simply by existing. JWST also discovered what astronomers nicknamed little red dots. Dozens of compact, intensely red objects scattered through the early universe, at distances corresponding to when the universe was only 600 to 800 million years old. These objects appeared to contain supermassive black holes, far too large for their age, surrounded by star formation at rates that stretched our current models to their limits. The universe grew up faster than we thought. Black holes formed sooner, galaxies assembled earlier. Something in our understanding of cosmic evolution needs revision, and the scientists working on this know it and are excited by it, because a model that needs revision is a model about to become more true. In 2025 and 2026, JWST continued observing, continued sending back light from distances and times that no previous instrument could reach. Each image a time machine, each time machine showing something that revised, complicated, or deepened what we thought we knew. This is what science feels like from the inside, not a steady accumulation of confirmed facts, but a conversation that keeps surprising you, where the universe keeps saying yes and also this, yes and also this. Now we have traveled far enough. Let me try to answer the question. We began tonight with something simple and strange, a question that stopped me one evening while watching the sun go down. What sits directly above the sun? What lies directly below? Here is the fullest answer I can give you. Above the sun, starting from its corona and moving outward, the solar wind flowing at hundreds of kilometers per second, the heliosphere, that deflated croissant-shaped bubble of solar influence, the local bubble, 1,000 light-years across, carved by ancient supernovae 14 million years ago, the interstellar medium, threaded with magnetic fields and wandering atoms of hydrogen, threaded with visitors from other stellar systems passing through on ancient trajectories. Above that, the sparse stellar halo of the Milky Way, where old stars drift in long, eccentric orbits, carrying the chemical memory of galaxies absorbed long ago. Above that, extragalactic space, where Andromeda drifts 2.5 million light-years away, already moving toward us in a merger that will take billions of years to complete, where the Laniakea supercluster flows across 520 million light-years, where JWST has seen the cosmic vine 12 billion light-years away, where the oldest light yet detected traveled for 13.4 billion years to reach us, and below the sun, the same, the heliosphere below, the local bubble below. The Magellanic Clouds below 160,000 light-years away, orbiting our galaxy. The halo below, and then everything, the full observable universe, extending in every direction, equally, without preference or hierarchy. The universe has no above and below. Those are human words. We invented them because we needed them, because without orientation, even curiosity collapses. We needed a map, even of a territory that has no such thing. But in searching for an answer to a simple question, we found something larger than the question itself. We found that the space surrounding our sun is not empty. It is layered. It is ancient. It is full of things. Comets falling from the Oort Cloud, visitors from other star systems, echoes of galactic collisions still propagating through the disk, a universe of galaxies clustering and flowing and merging and surprising us every time we look more carefully. And we found that sitting at the center of all of it, around a small yellow star in a quiet arm of the Milky Way, in the outer reaches of Laniakea, on the third planet from the Sun, living things developed the capacity to ask questions about their location in the universe. That is not a small thing. That might be the largest thing of all. It is time to go home. Slowly now. The way you return from a very long dream. Gently, without hurry. The way water finds its level. Laniakea contracts around us. 520 million light-years become comprehensible again. The Milky Way reappears below us, its spiral arms sweeping outward from the central bar, from the black hole we photographed in 2022, still spinning in its ancient silence 26,000 light-years away. We drift inward, through the stellar halo, where old stars move in their long, arcing orbits, carrying the memory of galaxies absorbed before our sun was born. Into the disk, into our own spiral arm, the Orion arm, where the density of stars increases, where the interstellar medium thickens, where the familiar constellations begin to resolve, past nearby stars. Proxima Centauri, 4.2 light-years away, a small red dwarf with its own orbiting planets. Alpha Centauri, slightly further, a system of 3 stars. Sirius, 8.6 light-years, the brightest star in our night sky. Vega, 25 light-years. Arcturus, 37 light-years, each one a sun. Each one with its own story, its own history, its own relationship to the galaxy's slow rotation and the ancient collision that still rings through the disk. And then our sun appears, growing from a point of light into a disk, warm and yellow and deeply familiar, the way a face becomes familiar not because it is exceptional, but because it is yours, because you have been looking at it your whole life. The solar wind surrounds us again, the heliosphere, the deflated croissant-shaped bubble of home, past Neptune in its slow 165-year orbit, past the ringed beauty of Saturn, past Jupiter, the great protector, whose gravity has been quietly deflecting objects that might otherwise threaten the inner planets for billions of years, past Mars, small and red and cold in the dark, and there, growing ahead of us, blue, soft, wrapped in its thin shell of atmosphere, lit by the sun from one side, dark on the other, the terminator line between day and night sweeping slowly across its surface as it turns. Earth. Here is what I want you to hold as you drift off tonight. You went somewhere enormous this evening. You left the heliosphere and crossed the heliopause. You visited the Oort Cloud in its silence. You drifted through the local bubble and the interstellar medium. You rose above the galactic plane and looked back at a galaxy still vibrating from an ancient impact. You located yourself inside Laniakea, that immeasurable heaven 520 million light-years across. You watched JWST find a vine of galaxies 12 billion years old, and now you are back, in your body, on your bed, on the third planet from an ordinary star. in the outer reaches of a barred spiral galaxy, in the outer corner of a supercluster, in a universe 13.8 billion years old that produced, through processes it did not intend and could not anticipate, something capable of wondering about all of it. Above you right now, as you breathe in the dark, everything we traveled through is exactly where we left it. The heliosphere is doing its quiet work. The local bubble is still hot and thin from the supernova that cleared it 14 million years ago. The Milky Way is rotating on its 225 million year circuit. Sagittarius A star is spinning at the galactic center, patient and dark. Laniakea flows outward in every direction, 100,000 galaxies drifting slowly toward the great attractor. And somewhere in the middle of all of that, bobbing gently through the galactic plane over tens of millions of years, a small yellow star keeps 8 planets in their orbits with nothing more than gravity. On the third one, there is a person breathing slowly in the dark. The universe is 13.8 billion years old. It formed from a state of such extraordinary simplicity that the entire observable cosmos once fit into a space smaller than an atom. Everything since then, every star, every galaxy, every collision and merger and explosion, every formation of a planetary system, every moment of chemistry that led to the first cell, every billion years of evolution that led from that cell to a creature who could build a telescope and then use it to photograph the black hole at the center of its own galaxy, all of that came from that first moment of extraordinary simplicity. You are part of that chain, made of elements forged in stars that died before our sun was born, living on a world that formed from the same ancient cloud, breathing oxygen that stromatolites produced billions of years ago, alive in a body shaped by billions of years of evolution. Conscious in a way that allows you to look up at the sky and feel something about what you see. That is not an accident. It is not insignificant. It is, by any reasonable measure, the most astonishing thing the universe has produced. Let your breath be slow. Let your thoughts be quiet. Let your body be heavy and warm and held. The Oort Cloud will keep its vigil. Voyager 1 will continue its long drift through interstellar space, its golden record aboard, carrying the sound of rain and a mother's voice into the dark. The Andromeda Galaxy will continue its patient approach. JWST will keep gathering ancient light. None of it needs your attention tonight. The question we started with has been answered as fully as it can be answered with the knowledge we have right now. Above the sun and below it, everything. Layers upon layers of ancient, astonishing, beautiful everything. And right in the middle of it, improbably, briefly, impossibly, luckily, here, you. Just rest now. You are exactly where you belong. Good night.